Welcome back to our course on memory device technology for AI/ML computing. I am your instructor, Dr. Shubhadeep. So let's try to recall what we were doing in the last two lectures. We were primarily looking at global memory trends, and we saw that what is essentially driving these markets are the ability to innovate and the ability to innovate quickly. We saw that in several cases, such as in the SRAM, which is a on-chip memory, and also for DRAM and NAND flash, which were off-chip memory. We also saw that the share for on-chip and off-chip memory is almost the same. But a very interesting trend which we discuss later on is about electronic non-volatile memories or storage class memories, where we saw that a lot of new companies, including startups, are innovating in making new kinds of electronic non-volatile memories, and the amount of growth year on year that we are seeing for these storage class memories, which are designed to bridge the gap between memory and storage, is quite phenomenal. Okay, with this, we are in a good position to deep dive into individual memory elements. But as we had discussed, before we deep dive into individual memory elements, it may be worthwhile to look at a very important topic which gives us a holistic view of how memory design happens. And that is the topic that we will start today. It's a new topic on memory array architecture. So in memory array architecture, the fundamental question we will try to answer is that how are these individual memory cells, which store 1 bit of value, organized into large memory arrays, and how is the peripheral design around these memory arrays constructed to facilitate efficient read and write processes, right? So let us begin our lecture. Let's start from the very basics. In this slide, we will look at some very basic definitions which we will use for the rest of our course. So let's deep dive and focus on this. So what you see on the slide on the top left corner is a visual representation, a box representation of a single memory element. Single memory element can be defined as that which stores 1 bit of information. So that can be either a 0 or a 1. The question is, how is this memory element accessed? That is done through the data select or data access bit. So it is not that at the output the memory bit is always accessible. Only when the data select bit is enabled, then meaningful value is asserted on the data access bit. So natural question to ask is, does each and every small element or each and every bit have a data select bit? No, that is not efficient. What is done is a bunch of bits. Here we have shown it is k bits are organized in a fashion called one word, and we will soon see what a word means. And this data select bit, a single data select bit, gives access to one word of information. What is this one word? These are k individual bits organized in a row-wise fashion. So what is the value or what is the importance of a particular word? And this is the first technical term we will use. So as we just discussed, k bits or k individual memory elements are organized into one word. The value or the importance of this one word is that the computer or the CPU, which is going to access these data elements, generally sees one word of information. What this means is that the size of the CPU registers is generally worth k bits. It is of k bits. So earlier, if you remember, earlier CPUs used to have 32-bit processors. We used to have 32-bit processors. Now there is an upgradation and mostly we have 64-bit processors. And for really high intense AI/ML computations, there are specialized CPUs which also see 128 bits as a single word. So in essence, the CPU expectation from the memory unit is that when it asserts one address line, it should get in return 1 word worth of information or k bits worth of information. And therefore, the size of the data bus generally, in most general cases, is also worth k bits. So needless to say, since the expectation of the CPU is that you put one address and expect one word, every word in the memory array has one unique address. And that is what is defined by the select line. So here we will come to 2 other important definitions which we will be using throughout the course. That is the word line and the bit line. So what is the word line? The word line is essentially the data select input to the memory array. So when a word line is selected, the memory array understands that it's an indicator for which particular word line or which particular word is to be read out at the data output pins. And the data pins, which we see over here, the data access pin is essentially known as the bit line. So word line indicates which word has to be read out of the several words which are stored in the memory array, and the bit line contains the information which was stored in that individual memory element. And the best way to understand that is through this very simple array that I have presented in front of you. As we have been studying, that DRAMs consist of just one transistor, the access transistor, and one capacitor, and the storage node is where I am pointing out at the end of the capacitor and the drain of the transistor. So this we can say is a array of DRAM cells. So in this kind of array, what is connected to the word line and bit line? So as you can see, there are individual word lines which are these horizontal lines. These horizontal lines are the word lines, and they are connected to the gate of the transistor. And as we know, if these word lines are asserted, that means it goes from 0 to 1, this NMOS which I have indicated over here will turn on. So in essence, what the word line will do is enable the transfer of information, or it will create kind of like a connection or a short circuit between the storage node and the corresponding bit line. And what is this bit line? The bit line are these vertical lines which is running through the array, which is connected to individual bits of a particular word. So you have, as you can see, you have 4 different bit lines. Each are connected to individual cells. But please understand, the data in the bit line becomes valid or becomes relevant only when the respective word lines are turned on. And this is the very important concept of word line and bit line, which we will see throughout the course. So to further crystallize our understanding of what word line and bit line is, let us try to answer these questions for this simple DRAM array. So what I would like for you to do is take a pause in the video and answer these simple questions, which will help you in deepening your understanding of word line, bit line, and word length. So the first question is, what is the word length? The second is, what are the number of addressable words? Remember, the number of addressable words will be same as the number of select lines, or in our terminology or in our parlance, it will be the number of word lines. So what are the number of word lines, which will also be the number of addressable words? What are the total number of bit lines? So try to think whether the bit lines will be equal to the word length or not for this very simple architecture. So it looks like it should be the same. And finally, we will ask the question, what are the total number of cells in this array? But of course, for a simple array, you can actually count the number of DRAM cells. But how do you principally, for a bigger array, find the total number of cells? or total number of bits that can be stored in this memory array. So this is a time. Please take a short pause and try to answer these questions on your own. So here are the answers for the questions that were asked in the previous slide. As you can see, the word length of this entire array has to be 4, because when a particular word line, which is indicated by these horizontal lines, get enabled, it pushes out 4 data bits into the corresponding bit lines. Therefore, the word length and the number of bits or the number of bit length is the same in this particular array, and the number, as you can count, is 1, 2, 3 and 4. So bit line 1, bit line 2, bit line 3, bit line 4 will give you 4 bits of information, which in this simple array will be also the word length. What are the number of addressable words in this very simple array? As you can count, that number of addressable word lengths will be same as the word line, and in this case it will be 1, 2, 3, 4, 5 and 6. So word line 1, word line 2 across to word line 6. So this is the simple answer for what is the word length, the addressable words, which is the word length, and the number of bit lines. Okay. So the final question was, what is the total number of cells in this memory array? So one simple way is to count the total number of cells, and you will see it is 24. But a more fundamental way of coming to the same answer would be to recognize that there is one individual memory cell or a bit stored at the intersection of every bit line and every word line. So as you can see, at the intersection of every bit line and word line is a memory unit. And therefore, the total number of memory cells would be the multiplication between the number of word lines and the number of bit lines. And in this case, the answer comes out to be 24. Okay. So if we have understood this, this is a good start into understanding how memory arrays are organized. However, as we can see that 24 is a really small number for doing any form of reasonable computation. As you know, current day computing systems require several megabits or gigabytes of information to be stored into the memory array. So important question is, okay, this is a very nice diagrammatic representation, but how do you scale these memory arrays to include large parts of information or large amounts of information? And to understand this, today in this class, we will take a very simple example. We will take an example where you need 32 megabit of memory and the word length K is 32. So we are considering an older generation of technology where the word length was 32, and the expectation from the CPU is that there will be 32 megabit data. So it's very easy to see that if K is equal to 32, the number of select lines will be 10 to the power of 6, because 32 into 10 to the power of 6 roughly will give you 32 megabit data. So in other words, the number of bit lines should also be equal to 32, because each bit line will give you 1 bit of information, and the number of word lines will be 10 to the power of 6. So a simplest idea of how to organize this is to just simply stack everything vertically. That means from word 0 to word 2 right up to word 1 million is stacked vertically. Each word, as you can see, will have K bits, and that is the word length, and the number of select lines will be equal to the number of words. Each select line will be mapped to one word. So there will be, just like there are a million words, there will be a million select lines. So one important thing to notice over here when we design this architecture is that from the CPU, you will be sending out 1,000,000 select lines. Now please understand that is almost impossible. Just imagine two chips. One is your CPU and another is your memory. Remember, we studied this when we were looking at the von Neumann architecture. CPU and memory elements are separate and they are connected by address bus and the data bus. So entire responsibility of conveying which of the select lines, which one of the 1,000,000 select lines is to be accessed is on this, the onus is on the CPU. Now it is almost impossible to make sure that from one chip in a physical system there are 1,000,000 select lines which go from the CPU to the memory. This is a completely impractical design. So what is the solution for this problem? And for all of you who are very familiar with digital design, you will know that through a very simple digital circuit called the address decoder or the decoder, you can send two inputs and you can give, you can set n inputs and you can select one of 2 to the power of n outputs. This is the job of the decoder. A simple 2-bit decoder is presented for your information. Here you see there are just 2 bits of input, A0 and A1, and the truth table for A0 and A1, which of the select lines or data lines it will select is also given. If it is 00, it will select the first data line. If it is 01, it is the second data line, so on and so forth. So the equations and the truth table for a very simple circuit consisting only of NOT gates and AND gates facilitates the selection of 2 to the power of n. Here n is equal to 2, so 2 to the power of n is 4. Select lines from just 2 inputs. This is a scalable solution, and that is why the first or the simplest peripheral that you use to access the data in a memory array is something called the address decoder. So what is the job of the address decoder? It takes n bits from the CPU. From these n bits, it selects the one of the 2 to the power of n lines. It enables one of the 2 to the power of n lines, and the corresponding word to the selected line or selected word line is asserted at the output or the input. Okay, so this is how you make the problem of an impossible routing situation very simple by using an address decoder. And this is also the simplest or the first example that we see of the importance of peripheral circuitry. It is not enough to only organize these bits in an array-wise fashion. It is also important to have additional circuitry which can make communication to and from the CPU very effective. With this, let us go to our next topic. Let us review how this address decoder will work when it is implemented in very large arrays. But before that, an important thing that we should probably discuss is that please recognize that the address decoder is completely digital logic, whereas the array can consist of analog elements as well. So when you design these memory peripherals, few important points such as the pitch between the select line and the word line of the select line of the address decoder and the word line of your memory array needs to be matched both in size and in impedance. Otherwise, there can be a lot of switching losses and interconnect related delays. Having understood this, let's move ahead and try to understand how the address decoder, the simplest peripheral circuitry, will be used to organize a 32 megabit array. So here what we saw was if you had a 32 megabit array, the word line will be 10 to the power of 6 and the bit line will be just 32. So this is the representation, a more realistic representation of the following case. Please see the ratio of this particular array is so elongated. This array is very elongated and the ratio between word line or bit line and word line is 32 is to 1 is to the power 1e16 or 32 is to 1 million. So therefore, essentially the solution we have proposed is a rectangular array with really weird aspect ratios. So here we bring our first question. Is this really a very practical design? Is this a very good design? And immediately, if you think very carefully about it, you will see that no, this is not a good design at all. Why is this not a good design? First and foremost, just see what is the size of the bit lines. Individual bit lines are really, really long. Here I have indicated the 32 bit lines by these vertical lines, green vertical lines. As you can see, the green vertical lines are very, very long compared to the red horizontal lines which are representing the word line. As a result, try to imagine that the amount of time that it will take to read out the data or write the data from the first word will be drastically more than what will happen in the millionth word, right? And this will cause huge amount of read and write latencies. Furthermore, because the size of the line is very large, it will have additional resistances and capacitances. This will also cause huge amount of energy dissipation. We will soon see that although we are representing these lines with just these bit lines and word lines with just simple lines, in reality there will be a lumped circuit element consisting of both resistive and capacitive elements. So these resistive and capacitive elements, when you try to charge and discharge them, there will be lot of heat dissipation and ohmic losses. And this is the energy dissipation that we are discussing here. Finally, just try to imagine like a physical design of these arrays. As a physical design engineer, you will have a very tough time in organizing these arrays in your floor plan of your design. So if you remember when we were looking at how much area the SRAM cell consumes in modern day circuits, I had shown you some very fancy floor plans. The floor plans consist of different which area is allocated to different places in the chip. Just like whenever we go to construct or buy a house, we see the floor plan, which part belongs to the kitchen, which part belongs to the bedroom and the hall. Similarly, we have a floor plan for VLSI design also, which allots different areas to different parts of the circuit. Now, as you can understand, the floor plan for this kind of elongated, large aspect ratio structures will be very difficult to manage. And therefore, we say that this is not really a very good or a practical design. So what could be the solution to get rid of these problems? And the solution is very simple. Instead of having this long elongated structure where the problem was that you had a really weird aspect ratio. An aspect ratio of this rectangular array was 1 is to 31,000 odd. Can't we somehow fold this rectangular array into a more squarish array with an aspect ratio of 1 is to 1? That means that the sides of the array, which are here represented by the number of bit lines and the word lines, have to be equal. So the fundamental constraint we put into a effective design is to have a square matrix array with the number of bit lines and the number of word lines being equal. However, it is important to recognize that the expectations from the CPU still remain the same. The expectation from the CPU from the rectangular array was that it will be asserting 20 bits of address and getting 32 bits of data in or out. It will address one of the unique memory locations or words through this 20-bit address, and it should receive 32 bits of information. As you can easily see, in the previous rectangular array, this was easily facilitated by a simple row decoder or address decoder. As you can see in the current architecture or the squarish architecture, the same peripheral architecture will not work. So in the next class, we will try to see how memory arrays and the peripherals are organized to have a more squarish representation in the memory array. So let us finish this lecture at this point. So essentially what we saw in today's lecture was how memory arrays are organized through bit lines and word lines. The word lines consisted of one addressable word, and the bit lines consisted were the lines which were giving out the data corresponding to the selected word. We also saw how when you scale up arrays from the simple 24 array to a 32 megabit array, there is an increased need for memory peripherals. The simplest memory peripheral was a address decoder, and in the next class we will see how very quickly, as you scale these memory arrays, the complexity of your peripherals also start increasing. So let us stop here and see you in the next session.